me about what you know about a linear relation? Yes?
It's a straight line.
Yes. When we graph it, graphically, it is a straight line. Okay. What else?
It
Yes?
goes up or down by the same amount every time.
Okay, that is a very good point. Yes, that's almost exactly the definition of a linear function. Okay, so what Olivia just said was it goes up or down by the same amount each time. Okay, so I'm going to just refine that a little bit. A linear function is a function in which a constant change in the independent variable results in a constant change in the dependent variable. Okay, so I'm going to write that out, then we'll talk about it. Function in which a constant change in the independent variable results in a constant change in the dependent variable. So for example, if x goes 1, 2, 3, 4, 5, etc., and y goes 1, 4, 7, 10, 13, etc. Okay, let's just actually maybe is this linear? Yes, because there is a constant change in x. The constant change in x is that x is increasing by 1. That results in a constant change in y. Y is increasing by 3. Okay? Another way that I like to think about it is, would the change from x going from 1 to 2 be the same as the change in x going from 101 to 102, right? Regardless, the change in y is still going to be 3. Okay? So this is an example of a linear relation or a linear function. We're going to talk a lot more about these, and we'll talk a lot about different types of linear functions. We'll talk a lot about contexts and what we can tell from the equation, the graph, and the context all sort of together. And we are also going to talk about how do we tell if something's linear or not, okay, based on various different forms. So graphically, that one's sort of the easiest. It looks like a line. We may also have to look at a table of values and say, is this linear? And we may also have to look at just a description of a situation and be able to tell if that situation could be modeled with a linear function. Okay? So speaking about lines, there's 3 types, but actually I kind of like to think of it as 4 types. You can have a horizontal line, a vertical line, or an oblique line, which is slanted or sort of diagonal. And I like to think of this as when you move from left to right, you slant upwards, or when you move from left to right, you slant downwards. Okay? These are all linear relations, but they're not all functions. So which is not function or which are not functions? Yeah. Yeah, vertical line will not pass the vertical line test So the vertical line is a linear relation, but not a function. Okay? All right, so let's take a look at, at this example. Okay, the table of values and graphs show the cost of pizza with up to 5 toppings. Okay, so 0 toppings, $12, 1 topping, $12.75, etc. And we can see the graph that goes along with this data right here. Okay? So, can you write a rule that relates the cost of the pizza to the number of toppings? Okay, so some of you are already putting your hands up, but before you put your hands up, I want you to imagine that you are the person working at the pizza place and a customer calls and says, "Can you tell me how you do your pricing?" What would you say to them? Okay, yes.
Each extra topping is an extra 75 cents.
Yeah, okay, so that's one piece of it. Each additional topping costs 75 cents, and then what else? Yeah. Yeah, the base cost is $12 for the pizza, and then if you want additional toppings other than cheese, you have to pay 75 cents. Yes.
I have the formula.
Okay, let's do that. Let's write the rule first, and then let's talk about the equation. Okay, so base cost of a pizza is $12. Each additional, why can I not spell today? Topping costs 75 cents. Okay? Okay, yes, so you have an equation already. So tell me about the equation.
It's, I think, x equals y times 0.75 plus 12.
Okay, so I would say that's very, very close. Yes?
Y is equal to 0.75 x plus 4.
Yeah, so that's the only correction that I would make. If we're using the variables x and y, the cost is dependent on number of toppings. Okay? So if you're using the variables x and y, then you would have y equals 12 plus 0.75x. And we'll talk more about that in a second. But I would actually not use the variables x and y here, because I would prefer personally to use variables that will remind me of the context. So I might use c for cost and n for number of toppings. And in fact, n is a very common to use, variable to use rather, when the values that you can put in have to be whole numbers. Okay? Not always, but when you're counting a number of things, we often use the variable n. Okay? So to figure out the cost of this pizza, we have to start with $12, and then we have to add the cost of the toppings. Cost of the toppings is going to be 0.75 times the number of toppings that we have. So plus 0.75 n. Okay? Now, this is a very common theme when you're looking at pricing. Okay? So there is like a base cost, and this is called a variable cost. So we actually often call this the fixed costs variable costs. Okay? And in fact, we've already looked at some examples of this already. So I'm just going to sort of go back here and find, where is it? It's this one. This equation. Cost equals 25n plus 1,000. Right? So we looked at that example a few days ago, and we talked about the fact that the 25 represents the cost per person. So that would be things like food, things like, I don't know, party favors or whatever you're planning to give the guests. The 1,000 is your fixed costs. you have to pay that no matter what. So that's probably the hall rental and the entertainment and maybe the photographer or that sort of thing. Okay, so it still follows this same format. Our dependent variable is equal to the variable cost times the independent plus the fixed cost. Okay, and that's a very, very common structure to these cost situations. I think we're here. Okay, so you may want to write that down, that this is our fixed cost. And this is our variable cost. Okay? Yes? You sure?
Yeah.
Okay. How can you tell that the graph is linear? How can we tell that the graph is linear? Yeah.
It's a straight line.
Yeah. The points would form a line. Okay. Now let's talk about this. How can you tell from the table that this is a linear relation? Yeah.
That both variables increase in a constant rate.
Yeah, exactly. So how can you tell? Every time the number of toppings increases by 1,
And that was my question, actually. When you're writing these on a test, would that be a substantial answer?
yes.
Okay.
Every time the number of toppings increases by 1, the cost increases by 75 cents. Yeah. So I'm not going to write that all down, but that's exactly how you would justify that. Every time the number of toppings increases by 1, the cost increases by 75 cents. Okay? All right. So far, so good? Okay, let's look at this. So the relation between temperature in degrees Celsius, C, and temperatures in degrees Fahrenheit is in this table. Oh, I missed the beginning of the question. Which table of values represents a linear relation, and justify your answer? So here we've got a table of values that relates the temperature in degrees Fahrenheit to the temperature in degrees Celsius. And then the second one is a relation between a current and power in an electrical circuit. Okay? So I want to know whether these are linear or not. What do you think? Mm-hmm. Yes?
It's linear.
Okay, yeah, this one's linear. So if these are increasing by a constant amount, which they are,
5.
yeah, these are increasing by 5. So I go from 0 to 5 to 10 to 15 to 20. So each, okay, and then what happens here? Yep, it increases by 9. No, don't apologize. Okay, so this is linear. Okay, what about the second example? Nope. So these again go up by 5. Okay, these here, first it goes up by 75, and then it goes up by 225, and then it goes up by 375, and then it goes up by 525. Okay, so there doesn't seem to be, I suppose once you get past the 0, the change increases by 150, it looks like. But it's still not linear, right? Because we don't care about what's the difference here. We care about what's the difference in this column. Okay? So this is not linear. There's a couple of things that can trip people up sometimes. So I wanted to show you a couple of examples where Sometimes people say the wrong answers. So let's say I did this first. Okay. Is this linear? Yep.
It's not, because although it is multiplying by 2, it's not going up by the same amount.
Exactly, yes. So people sometimes get confused when they see a pattern, and there is a pattern here. It's a multiplication pattern, yes.
And if it helps you to visualize it in your head or quickly plot it out roughly, and you'll see that it'll make a curve, not a
Yeah, so you can actually take some scrap paper, plot it out, see it makes a curve. This is a pattern of repeated multiplication. Where do we see repeated multiplication? Yeah, exponents. This is an exponential function. Yeah. Okay, so there is a connection between the two variables. We can clearly define that algebraically. We can predict what the graph is going to look like, but if the question is just, is it linear? It is not linear, okay? So that's sometimes something that can trip people up. And then the other one is something like this. Okay, so let's say I have okay. Okay. What about this? This guy, right here. Is this linear?
Is the rate of change?
It sure is.
Not all the values on the x side are included, so it's a little misleading.
Exactly. So it's misleading because we are used to just looking at the change in x and comparing it to change in y. The problem is that in this table, there isn't a constant change in x, right? So here it's going up by 1, here it's going up by 3, then it goes up by 1, then it goes up by, it goes up by 2, then it goes up by 1, okay? This goes up by 3, this goes up by 9, this goes up by 6, this goes up by 3, okay? So the change in the x is not constant. But if you look at the proportionality, it is constant, right? So changes by 1, changes by 3. Now this changes by 3. This changes by triple that, okay? This changes by 2. This changes by double 3, right? And then it changes by 1 again, and this changes by 3. So, you want to make sure when you're looking at these that you pay attention to the x column as well, because if that is not changing at a constant, by a constant amount, then you may have to look at the sort of in-between values to be able to tell if it's linear or not, okay? So this is linear. Okay, so you guys can try these too. And they shouldn't take too long, hopefully. A table of values and how to look at a graph and distinguish linear, not linear, okay? But what we're going to do next is look at a description of a situation and try to figure out, could this be modeled with a linear relation or linear function? Okay, so here's the situation. A new car is purchased for $24,000. Every year, the value of the car decreases by $15,000. The value is related to time. Okay, where would you start with this? Some of you may just know. Yeah?
I turn it into an equation.
You would turn it into an equation?
Expression.
An expression? Okay, so how would you do that?
So you could do like cost equals 2,400 divided by 15%.
Okay.
That's, but like I.
So you are kind of, I think what you're trying to do is get to the finish line right away, right? But we may need to take some steps in between to figure out exactly what's going on. Yeah?
I don't know if it's similar to what Archer does,
Mhm.
but I actually do format it in an equation.
Okay.
Where I know, so I know that cost is what I'm looking, or sorry, yeah,
Or let's call it value.
yeah, value is what I'm looking for.
Okay.
And I know that it's automatically going 200 or 24,000 is my automatic like standard price. So I know
Uh-huh.
C is equal, or value is equal to 24,000. And
Yeah.
if I notice that it increases by 50% every year, then I know the year is going to be dependent, or it's going to be dependent on how many years it is. So I would say V is equal to 24,000 minus 0.15x, or I guess
Okay.
a variable for that. And then from there I know, okay, so it's going to be constant change because it's not an exponent and it's not being like.
Okay, so again, I think this crowd, and it's a common thing, is trying to race to the finish line because it's interesting. In a regular class, I have all these people who are like, this is what you should do, which is a tiny little baby step because we're trying to figure out what's going on here, right? So let's just take this, right? Yes, we're subtracting 15%, but we're subtracting 15% of the original value, not time, right? So what would you do to try and figure out the connection between these variables? Yeah.
Like what I would do is I would like first figure out like what 15% of 24,000.
Okay.
Because then that would like give me an idea like, oh, so like the first year it would be like this
Yeah.
number, and then you just
And then you compare. Okay, so you're doing like this. What does that look like? Table of values. Yes. Let's make a table of values and just play this out for a few years and see what happens. Okay? So here we go. If we make a table of values, we're looking at time and value. And this is in dollars. This is in years. Okay? So let's start with time equals 0. How much is this thing worth? $24,000. Okay. After 1 year, how would we figure out the value of the car? Yeah. Do we have an equation that we know is true, though? It's losing 15% of its value. Yeah.
Find 50% of 24,000.
Yeah, you find 15%. Yeah, find 15% of 24,000, and then you have to subtract that out, right? Okay, so 15% of 24,000. Do you guys remember how to calculate this?
0.15.
Yeah. So of means times. The percent has to be written as a decimal. And I believe that's 3,600. Is that right? Okay. Okay, so we have to now subtract 3,600. And so what is that? It's 2,000 or 20,400. Okay. Year 2. How much do we have to take out of the value? 15% of that, yes. It loses 15% of its value each year. So we got to figure out 15% of that. Now, we can do, there's two ways of thinking about this. One way of thinking about it is that we have to take away 15%. Another way of thinking about it is what percent of its value does it retain?
The first year it would retain 85.
Yeah. If it's losing 15% of its value, it's retaining 85% of its value. So if we want to know, instead of doing this, what it's going to be worth the next year, it's worth 85% of what it was worth the year before. So So this is actually times 0.85, right? Two ways of looking at it. One way is that you have to take away 15% to get the new value. Another way is you retain 85% of what you had. Okay? What's it going to be worth after 2 years? Yeah. How did you get that?
I just did 50%
Of the first year?
or no, sorry,
The second, yeah. So now it's only going to be worth 85% of this year. Right. Okay. So you can continue doing this, right? I don't know what the third one would be. Someone do that for me. Okay. This is not a constant change. Okay. This is also an exponential situation because we keep repeatedly multiplying by the same value, right? And this will come up in, this is a depreciation situation where the value of something is depreciating. That's very common for things like cars and things like electronics, TVs, phones, all that kind of stuff. It's worth the most the day that you buy it. As soon as you drive off the lot, it's losing its value. And so a lot of people like to buy a car that's maybe 2 years old because it's going to lose most of the value in the first 2 years, right? It loses more value going from here to here than here to here, okay? This can also, this kind of pattern happens also with things that are appreciating, like investments, right? So if you think about compound interest, you put $100 into an investment that compounds annually at a rate of 7%, right? After year one, you're going to have $107. After that, you're going to have 107% of 107. And so the idea is that your investment grows more and more and more and more each year, which is why, well, until it crashes. So, I mean, we're going to get onto a really big tangent right now, but I suppose the crashing situation, like, it depends on the amount of risk that you want to take and the length of your investment, right? So if you are investing like in the stock market or whatever, that can be risky and you have to watch quite closely as to the patterns of things going up and down and pay really close attention to economy and world events and things like that because things can change quickly, right? But you could also invest in like a mutual fund, which grow slowly but are fairly safe, right? And when you're investing in something like that, the idea is you're not investing in year one and taking it out 2 years later. You're going to put that money in and take it out 30, 40, 50 years later when you retire. And over that time, it will have had a chance to grow quite considerably, right? Okay, anyway, this is not linear.
We're not doing stock markets class.
Okay, let's take a look at this guy. For a service call, an electrician charges $75 flat rate plus $50 for each hour he works. The total cost for service is related to time. Yeah, so in fact, the other ones, the other example that we looked at, we could write that using an equation that relates the two variables as well. We're just not going to look at that this year, okay? But yes, this is a linear situation because we have a fixed cost, $75, and then each additional hour is going to cost an additional $50. So this is linear. If you wanted to make a table of values, you could, but if you also just know and you can explain why, that's fine, okay? Does anyone know what the equation would be that would relate cost to time? Yeah.
C is equal to 75 plus 50H.
Yeah, and typically you can write it, I could switch these two around. Typically you'll see when these are written out, and it's just habit, I guess. The fixed cost is at the end, and the variable cost that's attached to the variable, it's called the variable cost attached to the variable, is the first term. Okay, so this is our fixed cost. Why would the electrician charge $75 just to come to your door? Yeah, exactly, right? So if he only works, if he comes in or she comes in and it takes 5 minutes to fix whatever, you still have to drive all the way out there. You've booked that time off, so now you can't go and see someone else. And so it's still your time, right? And so typically there will be like a base fee for these types of services. Okay, so you guys are going to try these two. And then, yeah, we'll continue today. Rate of change. So we talked about linear relations. When you have a constant change in the independent, it results in a constant change in the dependent variable. And the rate of change of a linear function is the amount of change in the dependent variable per 1 unit of change in the independent. Okay? We'll see. Okay, so I'll give you an example. Let's say, oh, actually, before we talk about that, okay, so you just asked me about a ratio. That's a good question. So there's one distinct difference between a ratio and a rate. Does anyone know what it is? Yes.
I think a rate is like change per unit versus a ratio is like change compared to.
Okay, so you're very, very close. Yes. The unit thing is important. Okay, so anyone else want to hazard a guess? No? Okay, so a ratio is a numerical comparison of things that have the same unit. Okay, so if I'm comparing like how many apples to how many oranges, it's all fruit. I have 7 apples to 5 oranges. Okay, I may compare number of grade 10 students to number of grade 11 students. Okay, that's a ratio between grade 10 students and grade 11 students. The units are all people, students. Okay, a rate is a numerical comparison between two things that use different units. For example, kilometers per hour, which is a speed, right? A speed is essentially your change in distance compared to your change in time. Okay, so in fact, a rate of change should really be called almost a unit rate of change, because we want to know how much is the dependent changing per 1 change in the independent variable. Okay, so for example, if you travel 100 kilometers in 2 hours, what would your rate of change be? What would your rate of change be? Yep. 50 kilometers per hour. Per 1 hour, you're traveling 50 kilometers. Okay? The rate of change is 50 kilometers per hour, right? This is per 1 hour, but you don't have to put the 1 in there. Okay, so generally speaking, we can sort of summarize this as the rate of change is equal to change in dependent over change in independent. Now, well, not typically, but if we want to make a generalization, let's call the dependent variable y and the independent variable x. So we often write this as delta y over delta x. Okay, have you seen that delta symbol before?
Yep.
Yeah, it comes up a lot in chemistry, I think. Change in temperature, change in whatever.
Physics, but yeah.
Physics too, yeah. What does it mean?
Law one physics and law.
It means change.
Change. Yeah. So we use that in math too. Okay. It's actually a Greek letter. Alpha, beta, gamma, delta, epsilon. I don't know. I had them memorized at one point. I don't remember them anymore. I should do that. That's what I'll do over spring break. Okay. So, but typically though, now one thing I will mention is that we are going to see this come up in our next unit, and we're going to call it slope. This will dictate the slope of the line. How steep is it, right? The steepness of the line is really telling us how much the dependent is changing compared to the independent. So we also call this slope. Okay? So when do we use each one? To be honest, there is not really a distinction. They're kind of interchangeable. Okay? However, if you were talking about a context and you're talking about the slope of the context, you have to include units in there. I don't just want to say the rate of change is 50. 50 what? Right? 50 kilometers per hour. So I prefer to think of it in terms of rate of change when there's a context attached to it, because it reminds me to include variables in my change in y over change in x. Okay? Some of you may have also seen graphically okay, if I'm looking at a graph and here's point 1 and here's point 2, and we want to know the change in y, that would be the change in y. That's the change in x. Okay. We call graphically the change in y the rise. And we call, the change in x the run.
The memories from science.
So rate of change, or sometimes if it's slope, we use the letter m, is rise over run. Okay.
And then when you're doing that, when your equation of y equals mx plus b, that's what you substitute.
Exactly. Yeah. And actually, I'm going to go a little further here and talk about, well, this is really great. Okay, rate of change, we can say exactly what it is when we have something like you travel 100 kilometers in 2 hours. Okay, when we can see graphically, okay, I can count how much to go up from here to here, how much to go from here to here, right? That I can see. What about if we just have 2 points and we wanted to determine the rate of change, okay? So I actually do want to go into this, and I think I'm going to do it on a new page because I'm just running out of space here. And I'm also going to add in some graph paper. Come on, there we go. Okay, there we go. Perfect. Okay, so really I'm just having this here as a tool. Okay, so if I asked, for example, what is the slope of the line segment, rate of change, I could say, connecting A, which is, let's say, -2, 6, to B, which let's say is 3 and 20. Oh no, that's too high. 6, no, that's too high. I'm trying to make up a good number because this is just off the cuff. Okay, I'm just going to put in, I don't know, 8, whatever. Okay, so we're going to connect those 2 points. We're going to figure out the slope. Okay, so based on what we've looked at so far, we would have to kind of plot these and then count out our rise and our run. Does that make sense? Okay, let's do it. So if I plot point A, then it's at -2, 6. So that's -2, 2, 4, 6. Okay, there's A. And if I plot point B, it's at 3, 8. 2, 4, 6, 8. There we go. Okay, and I am going to, here's A, here's B. I'm going to connect those. And this is the point 3, 8, and this is the point -2, 6.
So when you're doing this, you just organize it as a fraction, right?
Okay, so what is my rise?
The rise is 2.
Yes, the rise is 2. Right, so this is 2. And what about my run? 5. Right, okay. So the slope here is rise over run. Which is 2 over 5. Okay, no problem, all good. But it takes a long time to have to graph these points and count. So I want to talk about how can we get to the rise over run just looking at the coordinates of the points. Okay, let's think about that. So the rise is coming from the height of the points, which would be the y-coordinate of each point. So the rise ended up being 2. Our y-coordinates were 6 and 8. How do you get a 2 out of 6 and 8?
8 minus 6 is 2.
Yeah, exactly. So you can think of m being 8 minus 6 over, our run was 5. How do I get a 5 from, that's our horizontal, our x-coordinates, from a -2 and 3? 3 minus -2. Change, difference, subtraction, right?
We did this in science too, actually.
Okay, there's our 5 over 2. Now more generally, let's suppose this wasn't a coordinate at all. I'm just going to call this our first point is x1, y1. And our second point is x2, y2. Okay. Well, the 8 minus 6 was y2 minus y1. That's our change in height. Okay. Our 3 minus -2 is our x2 minus x1.
Yeah, didn't we use this for like calculating cell size or something?
Yep, this was like the exact thing, or like
Yeah.
finding the difference.
Yeah.
Points on a graph.
There you go. So
Awesome for all science, those sheets.
there are, you would have seen this in lots of contexts because lots of contexts are modeled with linear functions. Okay. Now, we have several ways of getting the slope or the rate of change. Okay. You will use all of them at some point. It just kind of depends on what you're working with, right? So if you're told in words 50 or 100 kilometers in 2 hours, you could probably work that out, right? If you have a graph in front of you, you can just do rise over run. And if you have points, you can use this slope formula. Okay, and you just kind of think about what's going to make it most efficient for you. Okay, and this kind of thing, by the way, the slope formula, we're really going to get into more of that in our next unit. We're going to focus more on it then, but I like to introduce it while I'm introducing slope because it's all the same thing. Okay, let's go back. Okay. Let's look at some examples. So a water tank on a farm near Swift-Current, Saskatchewan holds 6,000 liters of water. Graph A represents the tank being filled at a constant rate, and graph B represents the tank being emptied at a constant rate. Okay? So first we're going to identify the dependent and independent variables. And then we are going to determine the rate of change of each relation and what it represents. Okay? So let's start with dependent, independent variables. Which is which? Yep.
Time's independent and volume is dependent.
Yes. Okay. All right, rate of change. So if we look at graph A, right? And we want to think about our rate of change, we need to think about change in y over change in x. So here I would use rise over run, right? You can pick any 2 points you want. So typically, a lot of people like to use the end points, but you don't have to. If I'm looking at these 2 points and I think, okay, I'm going from 0 to 6,000. What's my rise? Yeah, so my rise is 6,000, but the only thing that I would recommend doing, particularly since this is a rate of change situation, is to include units. 6,000 liters. Okay? And then my run, I go from 0 minutes to 120 minutes. So the run is 120 minutes. Okay? So my rate of change is 6,000 liters per 120 minutes, which is, I believe, 50 liters per minute. Oh, this should be a minute there, per minute. Okay? What does that mean? When you're talking about what it means, you really just want to connect back to the units, right? Every minute, the volume of the tank increases by 50 liters. Okay? Okay, let's look at graph B. Okay, so if I go, let's say, from the endpoints again, from this point to this point, what direction vertically do I have to go to get from this point to this point? Down. Yes, okay. So if I start at 6,000 and I end up at 0, what do you think my change is? Yes, it's negative, okay? So these rise over run things, there are signs associated with direction. Up is positive, down is negative. Right is positive, left is negative, okay? So this is negative 6,000 liters. And my run is from left to right, and that's 60 minutes. So the rate of change here is negative 6,000 liters over 60 minutes, which is negative 100 liters per minute. Okay? And this, basically, the negative value tells us that the volume is decreasing. It's decreasing at a rate of 100 liters per minute. That make sense? All right, so you guys try the next one. Where the graph touches each axis. The x-intercepts are the value of x when the graph touches the x-axis, and the y-intercept is the value of y when the graph touches the y-intercept, or the y-axis rather. Okay? So for example, right, if you have, I don't know, let's say this is negative 2 and 2. and this is 1.5. Okay? This has 2 x-intercepts and 1 y-intercept. Okay? The x-intercepts are -2 and 2, and the y-intercept is 1.5.
And the intercept refers to the axis, not the point, right? So when you're
Yes.
saying x-axis is x.
Yes, the x-intercept refers to what is the x value when it hits the x-axis. Let's think about that, though, the coordinate point. Okay? When you are on the x-axis, wherever you are, you should know one of the 2 coordinates of your point.
0,
Yeah, which one is 0?
x, y.
The y, because you're at a height of 0, right? If you're on the x-axis, wherever you are, y is 0. Okay? Okay, so is the value of x when the graph touches the x-axis. Okay, now this is the most important thing to remember. When you're on the x-axis, y is 0. Okay, if you're on the x-axis, vertically, you're at a height of 0. So y will always be 0 on the x-axis. Right? Think about it. No matter where you are, this is 0. The y value is 0.
Okay.
Okay? Now, y-intercept is the value of y when the graph touches the y-axis. Okay? Now, wherever you are on the y-axis, again, you should know the value of one of the 2 coordinates. Which one do you know? Yeah, x is 0, because if you're on the y-axis, you're not going anywhere horizontally. So you're always at a horizontal value of 0. So here, on the y-axis, x is 0. Okay, now this is kind of a really easy way, actually, of graphing a linear relation. So I want to talk about that. And then I want to go back and look at context. And because there's a few things that are often really important and tell us something about the context in a linear situation. One of them is the rate of change, but the other ones are the intercepts. Usually something's going on there. Okay? So firstly, let's look at this guy. Use intercepts to sketch a graph of the linear function f of x equals 4x minus 3. Okay? So if you wanted to use intercepts to do that, well, if you want to graph a line, you only need 2 points. Then you connect the line and you get your points, right? So the y-intercept is when x equals 0. So we would want to know what's f of 0. Okay. The x-intercept is when y is 0. So we want to know what's x if f of x equals 0. Okay. Let's start with this one. If x is 0, what's f of x? Yeah. F of 0 is 4 times 0 minus 3, which is negative 3. So I'm going to draw some axes. Try and be as straight as I can. Okay. And then I have the point 0, negative 3. There's my y-intercept. Okay. This guy, okay, at the x-intercept, y is 0. So I'm going to sub in a 0 here and solve for x. Okay, and when I do that, I have to like add 3 to both sides. So 3 equals 4x, divide by 4. Okay, so x will be 3/4. So my x-intercept is right here. Okay, as soon as you have 2 points, you can connect them. There you go. So far, so good? Okay. Depending on the format of the equation, sometimes this is like the easiest way to graph. So this equation is linear. We could solve it for y, and it would be a linear equation. But it's actually written in a different format called standard form. We're going to learn more about that next unit. But when it's written in this way, it is super easy to figure out the value of x or y when the other one's 0. Right? So if you want to know, in this example, what the y-intercept is, put a 0 in for x. If you want to know what the x-intercept is, put a 0 in for y. Okay? Now, if x is 0, that term goes away. 3 times 0 is 0. So to solve for y, we have to think, okay, 2 times y is -6. What's y?
-3.
Right. And if y is 0, this term goes away. 3x equals -6. What's x?
2. Oh, wait.
-2. Okay? So we just have to plot those points. So when x is -2, y is 0. When x is 0, y is -3. There's our line.
More questions like these somewhere?
Are there more questions like these?
Yeah.
I think so. In your homework, there should be. Okay. And then similarly, with this guy, when x is 0, we're solving this. -9y equals -36. What's y? 4. Yeah.
Do you see questions that aren't in this format,
Will we see questions that are in this format?
that are not in this format?
Well, so I could ask you to determine the intercept for a linear function in any format. And the key thing to remember is that if you're on an intercept, you know one of the 2 coordinates.
Okay.
Either x is 0 or y is 0. In this particular format, it's very easy to graph from this format. But regardless, you just have to sub in a 0 for one of them, and then you're going to be able to solve for the other. Okay? Okay, when y is 0, I'm solving this. 6x equals -36. What's x? -6. Okay, so I got to plot those 2 points. -6, 0, 2, 4, 6. There we go. And 0, 4. There we go. There's the second one. Okay. Now, to wrap this up, though, I want to go back to the previous page so that we can actually talk about why these intercepts are important in a context. Okay, so here's a situation. Float planes fly into remote lakes in Canada's northern wilderness areas for ecotourism. This graph shows the height of a float plane above a lake as the plane descends to land. Okay, so first question. Where does the graph intersect the vertical axis? 1,000 meters. What does that represent in this situation?
That's the maximum height.
The y-intercept. Connect it back to the context, though. Remember, when you're on an intercept, you know the value of one of the 2 variables. So the height is 1,000 meters. What about the other one? Time is 0. So this tells you the initial height of the plane. Okay, so right, since time is 0. Okay, and then let's also look at the horizontal intercept. intersect? Okay, so where does the graph intersect the horizontal axis? 10 minutes. What does this represent? Yeah, the time it takes for the plane to land. Because if the plane is at a vertical height of 0, it's on the ground, right? So time it takes for the plane to land. Right? Those are pretty important pieces to this context. If you were describing to someone, well, it wouldn't be me because I would never fly a plane, but if it was a pilot, right, they may say to their traffic controller, I'm at an altitude of 1,000 meters, I think it's going to take about 10 minutes to land, right? So both of those pieces would go into a conversation about this context, okay? Finally, let's talk about the rate of change. Okay, so think about change in height over change in time. What is the change in height of this plane? Negative 1,000 meters, yeah. Whoops, I forgot a 0. And because it's descending, it's going down. And the change in time is 10 minutes, right? So the rate of change is going to be negative 100 meters per minute. Okay. Now, when you're describing this in words, you probably wouldn't say the rate of change is negative 100 meters per minute. You would probably use the word descent. It's descending at a rate of 100 meters per minute. And the word descending implies that that rate is negative because it's decreasing. Okay. Finally, let's talk about the domain and range. And then I think we'll leave it there for today. Okay. So domain. Domain is our time values. What's the smallest time and what's the largest time? 0 to 10, yeah. So for the domain, zero is less than or equal to time, which is less than or equal to 10. Or you could use interval notation here if you wanted. Like, I'm just trying to, anecdotally, I'm thinking to myself, in a context sort of thing like this, I don't usually see interval notation. It's usually sort of more abstract. But I suppose, unless I specified, you have to use inequalities, you could use interval notation if you wanted. And then, okay, what about the height? What's the minimum height? What's the maximum height? Yeah, so this is our domain. Our range is 0 is less than or equal to height, which is less than or equal to 1,000.
Would it be, just like for general application, better to use interval notation or set notation or?
I'm trying to think of how to answer that. Would it be better to use one over the other? So for the purpose of this course, unless I specify, I really don't care, right? I think the only reason why in a context you typically see the inequalities more is think about describing a context conversationally, right? How would you talk about the domain, right? You would say, you know, it goes from 0 to 10 minutes or something like that. So I suppose it's more sort of easily understood by everyday people who aren't taking math in high school or beyond to use inequalities. And that's probably why we use them more in contexts. But I honestly, if I don't specify, I don't care. Okay? All right, so I'm going to stop there for today. Oh, wait. There we go. Okay, and you guys can try this last question. And then